All right, today we are diving headfirst into the absolutely vibrant world of coordination compounds. We're going to unlock the secrets behind some of the most beautiful and most important substances in all of chemistry. So let's get right into it.
It all kicks off with a really simple question. Have you ever wondered why, say, a solution of copper sulfate is this brilliant, stunning blue, but something like table salt is just, well, plain white? What is it that gives some chemical compounds these spectacular colors? That's the exact mystery we're going to unravel today.
So our story here begins where a lot of great science stories do, with the early theories. The very first attempts by chemists to get a handle on these really unique and colorful structures. Okay, so this guy, Alfred Werner, a real pioneer in this field, he made a huge leap forward. He was the one who correctly figured out their basic architecture. He nailed down the number of groups, or ligands as they're called, that are attached to that central metal atom. And look, understanding that was absolutely foundational. But, and this is a big but, it was only part of the story. You see, Werner's theory, as great as it was, left two massive questions just sitting there on the table. For one, why are they so colorful? It had no answer. And two, what determines their magnetic properties? Again, nothing. The mystery actually got deeper. In science, well, it needed a whole new set of clues. So, the first major breakthrough in this whole chemical detective story, it came from one of the absolute giants of chemistry. He proposed a totally new idea. What if it was all about sharing?
And that brings us to valence bond theory, or VBT for short, championed by the legendary Linus Pauling. The core idea here is simple. The bond is purely covalent. Just imagine the ligands as being super generous, donating a pair of electrons that they then share with the central metal atom. It's like a cooperative, shared relationship. So, okay, how does this actually work? Well, the ligands offer up their electrons, right? Now, to accept them, the metal atom has to do this little shuffle with its own electron orbitals, a process called hybridization. It's basically creating new perfectly shaped slots for those incoming electrons. And this whole process is the key, because the specific type of hybridization, and don't worry about the crazy names like d²sp³, that directly locks in the compound's 3D shape, its geometry. In many cases, it creates a perfect octahedral.
And let me tell you, VBT was incredibly successful. I mean, it beautifully explained why these compounds have the specific shapes they do. It could even predict some of their magnetic behaviors. It was a fantastic theory. But there it is again. It still couldn't crack the code of color. The biggest piece of the puzzle was still missing.
So, to finally solve this nagging problem of color, science needed a completely different perspective. A new way of looking at it. One that treated the chemical bond not as some kind of shared friendship, but as a field of pure, raw electrostatic force.
And this is crystal field theory, or CFT. And CFT just takes that whole idea of sharing electrons and throws it right out the window. Instead, it assumes the bond is purely ionic. It wants you to imagine the ligands as just little negative point charges, and the metal as a positive center. They're attracted to each other purely by electrostatic force, kind of like tiny little magnets. Okay, so let's just pause and look at the direct contrast here, because it's fascinating. You've got VBT on one side saying the bond is covalent, and it's all about orbital hybridization. Then you've got CFT on the other side saying, nope, it's ionic, and it's all based on something completely new called d-orbital splitting. I mean, these are two radically different explanations for the exact same thing. So what on earth is this splitting they're talking about? Okay, picture this. The metal has 5 d orbitals, and to start, they're all just sitting there at the same energy level, nice and equal. But then, as the ligands approach, their negative electric field starts to push back on the electrons in those orbitals, and everybody's energy goes up. But, and this is the absolute key, the repulsion isn't equal. The orbitals that are pointing directly at the incoming ligands, they get repelled way more and their energy shoots up. Meanwhile, the orbitals that are kind of nestled between the ligands are less affected and they actually drop to a lower energy state. And boom, just like that, you've created an energy gap. And that energy gap, that little space created by the splitting orbitals, well, it turns out that is the final clue we've been looking for. This is the key that finally unlocks the code of color.
So what we're looking at here is a phenomenon called a DD transition. Here's how it works. When light shines on the compound, an electron sitting in one of those lower energy d orbitals can absorb a very specific amount of energy, which corresponds to a specific color of light, and use that energy to make the leap up to a higher energy d orbital. That single jump, that's the whole secret right there. Okay, let's make this real with a perfect example. This titanium complex right here. It has just one single electron in its d orbitals. And that lonely little electron is just sitting comfortably in the lower energy level, that T2G set. It's basically just waiting for a little boost of energy.
So when white light, which remember contains all the colors of the rainbow, shines on the solution, that lone electron sees its chance. It absorbs a photon of light with a very specific energy, an amount that chemists measure as 20,000 inverse centimeters. That is the exact, precise amount of energy it needs to make that jump across the gap to the higher orbital. And here it is. This is the magic moment, the aha moment. The energy that electron absorbed corresponds to the yellow-green part of the light spectrum. So think about it. If the compound is basically eating the yellow-green light out of the white light that's passing through, what's left over for our eyes to see? Well, it's the opposite, the complementary color. And the complement of yellow-green is a beautiful, vibrant purple. And just like that, mystery solved. So there you have it. We've cracked the code of color. But this is so much more than just a fascinating piece of chemical theory. As we're about to see, understanding these compounds is absolutely fundamental to understanding, well, everything. Our bodies, our technology, and the world all around us. I mean, let's just start with life itself. You know the deep red color of your blood? That's hemoglobin, an iron coordination compound whose job is to carry oxygen. What about the green of every plant you see? That's chlorophyll, a magnesium complex that turns sunlight into energy. We are quite literally powered by this chemistry. And in medicine, these compounds are absolute lifesavers. Cisplatin, a platinum complex, is one of the most powerful anti-cancer drugs we have. Or think about lead poisoning. A special ligand called EDTA is used, and it acts like a tiny chemical claw, grabbing onto the toxic lead atoms and forming a stable complex that your body can then safely get rid of. Modern industry relies so heavily on them. You have special catalysts, like the Ziegler-Natta catalyst, that are essential for making the plastics we use every day. The process to get ultra-pure, 99.5% nickel? Yep, that involves a coordination compound. Even extracting precious metals like gold and silver from their ores depends on this exact chemistry. And it's in the technology all around us, even in places you might not expect. Remember old-school film photography? A coordination compound was used to fix the image, basically making it permanent. And next time you see a beautifully silver-plated or gold-plated object, you can bet it was made using a bath containing these compounds to get that perfect, smooth, uniform finish. So think about where we started. A simple question. Why are things colorful? Led us all the way to the fundamental chemistry that runs our bodies and builds our modern world. It really makes you wonder, doesn't it? If a model that simplifies a chemical bond down to just simple attraction can unlock so much, what other elegant, profound truths are out there just waiting to be discovered, hiding right beneath the surface of what we see every single day?